For number 9, evaluate the function for the given value of the variable. So for this one, I need to take the 5 and plug it in for this x right here. So I'm going to say f of x equals 3 to the 5th power. And to evaluate that, you're saying 3 times 3 times 3 times 3 times 3, so 5 times. And we get 243. Okay. And then in part B, we have h of t equals 5 times 2 to the negative 2 power. Well, we've been taught we cannot have this negative. So we put the expression over 1. The 5 would stay, and the 2 to the negative 2 would move to the bottom. So this 2 to the negative 2 become positive 4, and that 5 would stay. And then since we're not doing anything with this further, like graphing it, we can just leave it 5/4. Okay, in number 10, we have a population of amoebas that are going to triple in size every 20 minutes. Then, and the experiment starts with 600 amoebas. How many amoebas are in the petri dish after 2 hours? So first thing, let's convert hours to minutes. So 2 hours times 60 minutes is 120 minutes. Secondly, I know that within this 120-minute time period, every 20 minutes, the experiment, or the amoebas will triple in size. So I need to divide this by 20-minute periods. So here those zeros cancel out, and 12 divided by 2 is 6. And this represents our x value right here. So step 3 is to plug 6 into x and solve this equation. So y equals 600 times 3 to the 6th power. And so if I go ahead and do 3 to the 6th power, this gives me 729. I multiply these together, and I get 437,400 amoebas. Okay, lastly, number 11, we have to graph the exponential function. So here is our exponential function, f of x equals 2 times 3 to the x power. Again, f of x, that's your y. Okay? You don't think of it as f of x, you can think of it as y. And if I want to plug this into the table of values, I want to use -1, 0, 1 for x, because that's the dead center of my graph. Okay? So I want to work in this range right here. So now I need to start plugging in. So I'm going to have 2 times 3 to the -1. Again, can't have a negative. So I've got to put this over 1 and flip it. Well, 3 to the 1st power is 3. And it's important to know what decimal this is because I have to graph it. 2/3 is not going to help me. So even though I know that this is 2/3, if I divide that, we get 0.6 repeating. Now, if I plug 0 in, 3 to the 0 power is 1. So I've got 2 times 1, because 3 to the 0 became a 1, and 2 times 1 is 2. Okay, lastly, we have 2 times 3 to the 1st. Okay, plugged 1 into x. 3 to the 1st is 3. So I've got 2 times 3, and that's 6. So now I have to graph these 3 points. So for -1, starting at 0, I go -1, and I need to go up to about half, and then I just go a tiny bit above that. Okay, so a little tiny bit above half. At 0, we go to 2, and at 1, we go to 6. And then we have to draw this curve. It's not going to be a straight line. And what happens is when it gets to x, it gets really close to x. It's called it approaches x, but it never actually touches the x value, or the x-axis. All right, last one. So again, we're going to use the same numbers for x. Negative 1, 0, 1. G of x is y. Okay, it's all y. And then we start plugging in. So we've got 2 times 1/4 to the negative 1 power. So you have to kind of visualize that there's little ones right here. And if I multiply to negative 1, it becomes negative exponents. Well, I have to flip the whole fraction. And so it ends up looking like 4/1 to make everything positive. And if I divide that, we get 4. So 2 times 4 is 8. All right, then for the 0, this was really nice. We do 1/4 to the 0 power, and this whole thing becomes a 1. So we're going to say 2 times 1, and that's 2. And then for this one, we have 2 times 1/4 to the first power. So we have 2 times. Well, this 1/4 to the first power is 1/4. And if I make this a fraction, we multiply across. So 2 times 1 is 2, and 1 times 4 is 4. And what's 2/4 reduced? It's 1/2. Or you can think of it as 0.5, since we have to graph it on a graph. So I'm going to go negative 1, 8, put my point, at 0, 2, and then at 1 I'm going to go up to the half mark. And then I draw that curve, getting really close to x, but not quite getting there. And that is it.